Hi everyone, today I want to take you through the cross product. So the goal by the end of today's lesson is to be able to calculate the dot product of two geometric vectors and two Cartesian vectors or more. And just to learn a little bit of the intuition behind the cross product and how it's different from the dot product. Okay, we're also going to apply this in a couple different examples throughout the way. So let's get started. So firstly, the cross product between two vectors is another way, aside from the dot product, that we can find some sort of product between two vectors. And we're going to use a different notation, which is A cross B. And when we cross two vectors in 3 space, the result is actually going to be a vector that is orthogonal to both vectors that are being crossed. And just as a reminder, orthogonal essentially just means it's perpendicular to both vectors. So in order to figure out the direction of this orthogonal vector, we're going to use something called the right-handed system. So when we think about two vectors in space, let's say I like to use 2 pencils for my vectors. Let's say we have 2 vectors here. There's actually 2 resulting orthogonal vectors that we can get. There's one that comes out this way, okay, and it points in the upward direction, let's say. And there's another one that we could get that actually comes out this way and points in the bottom direction. So how do we know which is which when we cross 2 vectors? That's what the right-handed system is going to help us with. So the goal here is to take your right hand, and we always want our right hand to line up with the first vector in the cross product, and the tip of your fingers needs to line up with the direction of the vector. So if your vector is kind of going off in this direction, the tips of my fingers will be this way. If your vector is going in this direction, I'll make sure my tips of my finger are going that way. Now the goal here is to orient your hand in such a way that you can curl your fingers toward the other vector that you're crossing with. Okay. So if I curl this way, you'll notice that my thumb is pointing toward me. Whereas if I have to orient my fingers this way to curl this way, my thumb will actually be pointing away from me. So let's take a look at like an actual example that we can use this on. So let's just say vectors A and vector B lie in our page right now. So sometimes we just say like into the page or out of the page, just basically to give some kind of indication of direction. So we're going to say they lie in our paper right now or on our page. And if I do A cross B here, I want to line my fingers up with A so that the tips of my fingers point in the direction of A. And I want to be able to curl my fingers toward B. So this orientation of my hand seems to work well for that. I can curl my fingers toward vector B. Make sure you're trying it with me so you kind of get an idea. And notice that my thumb is pointing toward me. That's actually coming out of the page, right? It's starting, like imagine this is at the page, and then here's my vectors with my fingers. My vector is coming straight out, coming toward me. Now if I do B cross A, I'm actually going to have to orient my hand so that the back of my hand is facing up, and I'm pointing my fingers in the direction of B, and I want to be able to curl my fingers toward A. Now notice that my thumb is now pointing away from me, or it's going into the page. So A cross B is out of the page, whereas B cross A results in a vector that's into the page. So you want to pay attention to what your thumb is doing to decide on the direction of the vector. Okay, great. So out of the page and into the page. Now this is a little bit maybe difficult for us to visualize, so I want to take you over to GeoGebra so that you can get kind of a 3D image of what is going on here. So I just chose 2 random vectors here. I plotted them on GeoGebra. You can kind of see them here, vectors U and vector V. They have little labels. So let's say we want to do vector U cross vector V. Now I want to line my fingers up with vector V on my right hand, and I want to be able to curl my hand toward vector V. So I have my thumb pointing inward here, which means that our resulting vector should be kind of going back into that back quadrant there. So let's take a look at what that looks like. Okay, so we kind of see it here, and you can see that this vector actually is meeting both of the vectors at a 90-degree angle. Okay, so you can kind of see that from a couple different viewpoints here. And if we wanted to do V cross U, Then what I'm doing is I'm lining my right hand up with vector v so that the tips of my fingers are pointing in the direction that vector v is going, and I want to curl my fingers toward vector u. So the result is that my thumb is pointing back toward me, which means that our vector is probably coming into the quadrant that's closest to us, the front right quadrant there. So let's take a look. And there it is. So if I show you both of these vectors at the same time, you're actually going to see that they're collinear vectors. They simply just go in the opposite direction. So both of these are perpendicular to both vectors, u and v, and they simply just go in opposite directions. Let's take a look at a couple of properties of the cross product. So as we saw above, our cross product actually results in two opposite vectors if we cross in the opposite directions, or in the opposite order, I should say. So u cross v is going to be equal to the opposite of v cross u. I can do distributive property with the cross product, but I do need to be careful the order in which I do that. This is a main difference between the dot product and the cross product. The dot product, it doesn't matter what order I dot the vectors in, I'm going to get the same answer, but the cross product produces two opposite vectors, so it really does matter the order in which I cross the vectors. So you're going to notice in bullet points 2 and 3 kind of gives you an idea of this. So if I have u crossed with the sum of two vectors, I can distribute that cross product into the sum of the two vectors, but I do want to make sure that my u vector is actually the one being crossed first with v and w. Now you'll notice in the second bullet point that the cross product is actually after the sum of the two vectors. And I'm making sure that when I distribute that into the sum of the two vectors, that my vector w actually remains as the second component in that cross product. So just make sure that you're mindful about the order that you do the cross product in. A couple other properties are that if u and v are two non-zero vectors and we cross them and get the zero vector, this actually means that they are collinear. In other words, this means that they are parallel vectors and they lie on the same line, and they're scalar multiples of one another. Another thing that we can do is we can multiply the cross product by a scalar, and we can do this in any order as long as the order of the cross product stays the same. So I can do the cross product first and then multiply the scalar in. I can multiply the scalar by either one of the vectors so long as u and v remain in their same locations when I do the cross product itself. And then finally, the magnitude of the vector that we get resulting from u cross v is actually equal to the area of the parallelogram defined by u and v. And when I kind of go into a little bit more about why the cross product is how it is, you're going to get a better idea of why this parallelogram property is true. So before I go into some of the intuition behind dot versus cross and how that all works, we do need to know the geometric cross product formula. And the geometric cross product formula is the magnitude of vector A times the magnitude of vector B times the sine of the angle between the vectors when they're arranged tail to tail. You'll also notice that there's this little n hat on the end, and that is basically a normal vector, which means that it's a unit vector perpendicular to both vector A and vector B, as we saw as well in our Cartesian format. This is basically when we say normal vector, it's going to be a vector that's orthogonal to the vectors that are being crossed. Okay, so let's take a look at the dot product and cross product formulas. You might notice some similarities. Mainly, we are taking the product of the magnitudes of the vectors, and then we're taking either the sine or the cosine of the angle between the vectors. So we have to do something with that angle in order to find the product. You'll also notice that the cross product has something that the dot product doesn't, and this is this little normal vector, and that's actually indicating a direction. So this part is the magnitude of the vector, and this part right here is actually the direction of the vector. So the cross product, if you didn't pick up on this just yet, it gives us out a vector, whereas the dot product gives us out a scalar. So that's one major difference between the dot product and the cross product. And I want to take a look at kind of this, what is this cos theta and sine theta part? So let's take a look at two vectors. Let's say this is vector A and vector B. And we talked about the dot product kind of in a rearranged format here. So if I take the dot product and I rearrange it into B cross A, not cross A, times the cos of theta. What we said was that this little part here is actually the part of A that goes in the direction of B. So if we imagine kind of some sun rays shining down perpendicular to B, and the shadow that's cast is actually this part, A cos theta. It's the adjacent side if our angle theta is the theta between the vectors when they're arranged tail to tail, right? So we said that this is kind of like the piece of A that goes in the direction of B. This is A, magnitude of A times the cos of theta. So what this results in is kind of the product of how these components are working together. And that's basically what the dot product is trying to find. Okay, so if the dot product is how the vector components work in the same direction, that means that the dot product should actually be maximized the closer I bring this angle to vector B. So if vector A and vector B are collinear vectors, they get maximum components working together because they're actually working in the same direction. And we said that the dot product is actually equal to 0 when the vectors are perpendicular to one another. And that's because they have no components that are working together. One is completely vertical, let's say, and the other is completely horizontal. They're totally at opposite directions to one another, and there's no components working together. So now if we take a look at the cross product, let's just ignore this guy for a second. I want to focus in on this magnitude part. If I rearrange this, similar to what I did above, what is this A sine theta part in our diagram? Well, that's actually this part right here. It's the opposite side to theta. We've just rearranged SOHCAHTOA here, right? We've multiplied up the hypotenuse. This is equal to the opposite side if this is hypotenuse and this is the sine of theta. So this opposite side is actually the side that's perpendicular to vector B. So if I'm finding the magnitude of vector B and how it's perpendicular, or how the perpendicular component of A works with vector B, I'm kind of finding the product of the vector components and how they're working in a perpendicular direction to one another. And so that means that it's kind of like the opposite of the dot product, right? The dot product is looking at how much of A is going in the same direction as B. But the cross product between A and B is looking at how much, or at least the magnitude of that part, is looking at how much of A is working in a perpendicular direction to vector B. And this part of the drawing is actually part of where the that parallelogram property comes from. So I'm just going to move this so that I can draw the full picture here. Don't know if that worked properly. Okay, so if I create a parallelogram with vectors A and B, it's basically going to look like this. We're kind of used to doing this in vector addition. Now here's the parallelogram that's formed by A and B. So how do I find the area of a parallelogram? Well, the area of a parallelogram is actually the base of the parallelogram times the height of the parallelogram, and this needs to be the height measured perpendicular to the base. So the base here is actually the magnitude of vector B. It's going to be this length right here, right? It's going to be magnitude of vector B. And what's the height of the parallelogram? Well, it's actually this green line here, which is the magnitude of A times the sine of theta. So if I eliminate this normal vector part, I basically just have the magnitude of the cross product, And that's actually giving me the base of the parallelogram times that perpendicular height of the parallelogram. And this is where that property comes from. So hopefully this helps you understand the difference between dot and cross a little bit better. Okay, so let's actually apply this in a geometric scenario. We have vector u, which is 30 units, vector v, which has a magnitude of 20 units, and the angle between them, again, when they're arranged tail to tail, is 40 degrees. So if I do u cross v, I want to do magnitude of u times the magnitude of v times the sine of theta, and I'm going to put that normal vector there. So we're going to get 30 times 20 times the sine of 40, and we're going to keep that normal vector there. And if you're following along with us with your calculator, just make sure you're in degree mode, and you should get 385.67 units. And this part is the direction part. So remember, every vector has a magnitude and it also has a direction. So the normal vector, that little n hat part, it's going to help us with the direction. And we're actually going to decide right now if it's coming out of the plane of the page or if it's going into the plane of the page using the right hand rule. So line your fingers up with vector u. Notice that the palm of my hand is facing up. We want to be able to curl our fingers toward vector v, which means that your thumb should be pointing toward you. That means that this vector is coming out of the plane of the page. So we're going to say 385.67 out of the page. So for the second part here, we certainly are going to get the same magnitude of our vector. We're going to do magnitude of v times magnitude of u times the sine of theta times that normal vector. But basically when we enter this in, we do need to indicate that this is in the opposite direction as our calculation above. So I'm actually going to say minus n hat, just to indicate that this vector is the same as the vector above, but in the opposite direction. So what this means is that we're, sorry about that. What this actually means is we're going to get the same magnitude, that 385.67, but it's going to be in the opposite direction. Now, when we take a look at using the right hand rule here, this should make sense because we got a cat video bomb here. We're going to take our right hand and we're going to point it in the same direction as vector v. And we want to move our fingers so that we can curl them toward vector u. So lining them up with v, curling toward u. Our thumb is now going in the opposite direction as before, so we can say into the page for this one. All right, there we go. Okay, let's move on to the Cartesian formula for the cross product. And you will notice again that I'm only really showing 3D examples here because if I have two vectors, there is some sort of 3D component to this if I find their perpendicular vector. So we actually can't do the cross product between two 2D vectors. They need to have some sort of 3D element in order for me to find a third vector that's perpendicular or orthogonal to both of those vectors. So you cannot do the cross product with 2D vectors. Okay, so here's your formula here. I don't want you to use this formula. I mean, if you want to, you can memorize it, but it's a lot easier just to kind of do this setup that I've kind of set up for you above. So what you're going to do is you're going to take your first vector and write it twice. Once the second time directly after the first time, and then you're going to stack that with the second vector written twice. And then you're going to kind of follow this pattern. So you actually don't even need these two components. I usually just erase those or cross them out. And we're going to follow this top left to bottom right kind of direction here. And that's actually going to give us the first piece of x. And then we subtract with top right to bottom left product. And that's going to give us the second part of the x component of the cross product. Okay, so you're always going top left to the bottom right, do the product between those, and then subtract the top right to the bottom left. So same thing here, top left to bottom right gives you the first product, and top right to bottom left gives you the second product. Top left to bottom right, top right to bottom left. Okay, so once you do a little bit of practice with it, you're going to get the hang of it, no problem. So let's take a look at an example. We're going to do vector p crossed with vector u to start here. So what I'm going to do is I'm going to start by writing vector p twice, one after the other. And then vector q, I'm going to kind of like stack with that. Make sure you line everything up. Write it twice, one after the other. Now, like I said, we don't need this first and last row here, but it just helps to simply write the vectors twice, one after the other. So you can really just erase these parts here. We don't really need them. Okay, so to do each of the components of the vectors, we're going to go always top left to bottom right, find the product there. So we'll do 1 times 4. And then you subtract the product from the top right to bottom left. So -2 times 2. And then we'll move on to the next section of 4 vectors, these guys here. Okay, so you're going to do top left to bottom right, find the product, and then subtract top right to bottom left. Okay, and then the last block of vectors here, we're going to do top left to bottom right, subtract top right to bottom left. The biggest mistake that I see with this stuff is just getting confused between negatives and positives. People just try to do it too quickly, and then they mess up their cross product. So just be careful with that. Even if you have to write it out in a couple steps, no shame in that. So you might even just want to go through and simplify each component here, or each part of each component even, so that you make sure that you get it correct, especially if you're using this for another calculation. It can really kind of mess up your calculation if you're not careful. So you should get 8, -26, and 15 for this vector. Now, if you're going to do the opposite of that, q cross p, you would have set up with q written twice on top here. Oh, sorry, it'd be -1 and then 4. And then p, you're going to write that below twice. And that's kind of how you would set up your cross product. So you'd be essentially doing this for your cross product. However, you're going to notice here that when you kind of start to go along, you're actually simply getting the same products. So I'm getting 2 times -2, but then I'm subtracting the first component here. So you're getting 2 times -2, subtract 1 times -4. So you're really just swapping the order of those, which essentially is just going to give you the opposite of each of these. So you're going to get, instead of 8, you're going to get -8. Instead of -26, you'll get positive, and so on. So really the only impact when I do the cross product in the opposite direction, or in the opposite order, I should say, is that you get the vector in the opposite direction. So there's no need to really calculate it out again. You're simply just going to change the signs of each component in that vector. Determine the area of the parallelogram defined by vectors u and v. So I'm not really going to draw a picture of this, but just remember that the magnitude of that parallelogram is the area of the parallelogram is the magnitude of the cross product. So what we want to find is the magnitude of u cross v. And because we're doing the magnitude of the vector, it actually doesn't really matter whether I do u cross v or v cross u. But let's say I want to find u cross v to start here. I'm going to write out u twice, and I'll write out v twice. And again, we don't really need these parts, so you can just kind of cross those out, or you can erase them. Okay, so let's just take this piece by piece. This takes a little bit of practice when you're getting used to it, but once you have the hang of the little trick here, should be good to go. So just practice with it. So we're doing 5 times 7, subtract 2 times 2. and then move to your next block of vectors, 2 times 3. A lot of people do addition for these as well, like they'll go to do 2 times 3, but they'll do 5 accidentally, so just watch out for that. Minus 4 times 7. And then the last component, 4 times 2, minus 5 times 3. Great. And then we're just going to simplify this. So we're getting 35 minus 4, which gives us 31. 6 minus 28, which gives us negative 22. And 8 minus 15. So that gives us negative 7. So we do want to find the magnitude of this. So just as a reminder, we find the magnitude of a vector by taking the square root of the sums of the squares of each of the components. So you can take a second and enter this into your calculator. Again, ideally, we usually leave these answers as exact values where possible. So I'm getting the square root of 1494. And I can actually simplify this by, I think this is divisible by 9 as the biggest perfect square. So it's 9 times 166, which leaves us with 3 root 166. And we are finding area. So remember, area, when we have actual units like centimeters or meters, we always say centimeters squared or meters squared. So here I'm simply just going to indicate that this is talking about a measurement in square units. Okay, so you're always going to make sure you indicate that. Okay, and we're also going to figure out how we can use the angle between, how we can find the angle between two vectors using the cross product. So if you remember our geometric cross product, if I have u cross v, it's going to be the magnitude of u times the magnitude of v times the sine of theta. And if I want a direction aspect to that, then I usually multiply this by n hat. But I don't really need that part. So I'm simply going to focus in here on the magnitude of u, which is basically just this part right here without that normal vector part. So if I'm rearranging this, I'm just saying that sine theta is basically going to be the magnitude of u crossed with v divided by the individual magnitudes of each vector multiplied. So we've already calculated part of this. We found this to be 3 root 166. And then we're going to find the magnitude of u and the magnitude of v. So 4 squared plus 5 squared plus 2 squared. Let's just make this a little bit bigger so we can calculate that. And we're going to multiply that with the magnitude of vector v. So 3 squared plus 2 squared plus 7 squared. So for the magnitude of u, you should get root 45, and the magnitude of v, you should get root 62. So in order to find theta, we're just going to take the sine inverse of that in our calculator, and let's say we'll round to 1 decimal place here. Should get about 47.0, so we're going to say approximately 47 degrees for the angle here. Okay, this is another way that we can find the angle between two vectors. We also talked about how we can use the dot product formula for this as well. Okay, and just as a final example here, I want to find, I wrote A cross B cross A. Let's just say U cross V dot U. So I haven't written any brackets around these, and that's because I can only cross a vector with a vector, and I can only dot a vector with another vector. So if we think about this logically, if I did this piece first, I would actually get a scalar between that dot product, and then I wouldn't be able to cross vector u with that resulting scalar. But if I do the cross product part first, I'm going to get a vector, and then I should be able to dot that with vector u. So we actually already have found the cross product of v and u, And that was 31, negative 22, and negative 7. So we're not going to calculate that again. We're just going to write that here. And then we're going to dot this with vector u. And vector u is 4, 5, 2. So if we remember with the dot product, we just want to add like components of these vectors here. So and add their products. So I'm multiplying the y components and the x components and the z components and then adding them together. Okay, so what do we get here? Let's enter this into our calculator. So you should notice here that you actually end up with a dot product of 0. And this is a scalar, it's not the 0 vector because we do get, when we do the dot product, we get a scalar. But let's think about the intuition behind this. If I have vector v, now again, this is not going to be like accurate, but let's say I have vector v and vector u. Think about this in terms of 3D. If I cross them, I get a vector that's perpendicular to both of them. So it's going to be perpendicular to u, and it's also going to be perpendicular to vector v. Remember, this is in 3D, so imagine that this vector u is kind of like sticking, or this vector here is sticking up. Now, if I dot two perpendicular vectors, what did we say is the dot product of two perpendicular vectors? Well, the dot of two perpendicular vectors is actually 0. So from u cross v, I get a vector that's orthogonal or perpendicular to both u and v. And then if I dot it with u or even v, I should expect to get a dot product of 0 if I have done the cross product correctly, because I found a vector that's orthogonal to u.